This video considers different ways to solve stoichiometry problems. Dimensional analysis and BCA tables are two approaches. The kinds of scenarios we see with stoichiometry problems. Limiting reactants are a very common question type, and we want to be familiar with solving those. And there's other scenarios as well. Let's explore those ideas in this video. So when we have a stoichiometry problem, sometimes the information is in terms of grams, other times in terms of moles. We need to take information in grams and convert it to moles to get started. And if we're able to calculate the moles, sometimes we have to report that in grams. If we're making conversions between grams and moles, or between moles and grams, we're going to be using the molar mass. So we'll frequently be looking to the periodic table. The reason we have to have information in terms of moles is that in our balanced equation, moles are reacting with moles, or number of molecules with number of molecules. That's information that we get from the coefficients in our balanced equation. Here's a typical stoichiometry problem. Magnesium metal reacts with oxygen gas to produce magnesium oxide. If 56 grams of magnesium solid and 64 grams of oxygen gas completely react, what is the excess reactant, how much of it is left, and how much product is formed? Stop the video and give this a try. Grab a piece of paper, look to a periodic table, and write out your work. See if you're able to finish the problem. Here we have a balanced chemical equation for the reaction and converting the reactants into how many moles we have. Whatever approach that you're taking, I think this is absolutely your first step. Get yourself a balanced chemical equation, and if the information is presented in grams, convert that to moles. Let's figure out which one's the limiting reactant and which one's in excess. So in each case, if we know how many moles of a particular reactant we have, we can use the coefficients in the balanced chemical equation to figure out moles of product. This would be working it through in terms of the magnesium. The one below it, working it through in terms of moles of oxygen. Pause the video for a second. Do you have any questions at this point? Based on the information on the screen, can you identify the limiting reactant? If we analyze the amounts and we use the magnesium, we find that we can form 2.30 moles of magnesium oxide. If we use the oxygen, we could form 4 moles. That tells me that the magnesium is the limiting. The fewest amount of product is the amount that forms. So the oxygen is in excess, the magnesium is the limiting. All 2.30 moles of the magnesium are used up. How much oxygen remains? I'll set up another equation and find that all 2.30 moles of magnesium were used up. Based on the coefficient, 1 mole of O2 gas goes with 2 moles of magnesium. So I find that 1.15 moles of the oxygen gas is consumed. I started with 2. If I use up 1.15, I find I have 0.85 moles of oxygen gas remaining. To summarize what took place, we had a balanced equation and we first found moles of the reactants. We took each of the examples to see how much product would be formed and chose the one that identified the limiting reactant. For the excess, we then figured out how much of that reacted, compared it with then how much we initially had, took the difference between those, and found how much remained. Let's say we're doing the same thing with a BCA table. So for a BCA table, we initially have a balanced chemical equation. The first step is identical. Let's take the grams of the reactant and figure out moles that we have for each of the reactants, the magnesium and the oxygen gas. At this point, pause the video. Are you able to complete the rest of the table? What questions do you have at this point? Next thing we need to do is figure out which is the limiting reactant and which one's in excess. How do we do that? Well, we can just pick one of the reactants and try it out as the limiting. What do I mean as try it out? Let's say that we're going to use up all the oxygen gas. We start with 2 moles. Let's use up all 2 moles of it. How much magnesium would then be required? Using the coefficients, 2 moles of magnesium goes with every 1 mole of oxygen gas. How many moles of magnesium would we have if we used up 2? We would need 4 moles. Can we use up 4 moles? We can't use up 4 moles because we only had 2.3 to start. So it's not the oxygen that's the limiting, it must be the magnesium. If you've used up more than you started with, you've chosen the wrong one. So just choose the other one. We now know that we have to use up all of the magnesium. We know how much magnesium was used and how much oxygen was used. We see our proportion down here at the bottom. Pause the video. Do you have any questions at this point? Try to complete the rest of the BCA table. And there's my completed BCA table. The steps within this, we once again needed a balanced chemical equation. We figured out grams to moles using molar mass. Within the BCA table, we figured out the limiting reactant in excess just by picking one and trying it. And then we can complete the rest of the table to see what we have after the reaction. So here I show a summary of the 2 different approaches. The top, the BCA, and the bottom, the dimensional analysis. This is just work from the previous slides. I'm curious what you think. If you pause the video, which of these do you think would be the approach that you would use? Which one makes more sense? Are there parts that you're still confused with? Both of these lead us to the same answer. For me, I like the BCA table just because I can see all the information in stages and it allows a good check to see if I'm doing it right. But I'm curious, what's your view? Here's the worked example of a BCA table from the textbook. When they introduced BCA tables, this is the example that they used. Now, when I looked at this example, it's clear that in that scenario, the H2 gas, the hydrogen gas, was completely used up. That was the limiting reactant. What if you had that same information, but you weren't sure which one was the limiting reactant? Remember the strategy? Just pick one of the reactants and use it all up. So let's say you decided to use up all of the oxygen gas. That quickly reveals that you would need to use 14 moles of hydrogen gas. Can you use 14? No, you only have 10. So you've chosen incorrectly. Just erase that. Choose the next one. It must be that the hydrogen gas is the limiting, and sure enough, that's what's used to complete the rest of the table. One thing I like about the BCA tables is it gives me a really quick check. By simply calculating that change line and doing a comparison, it allows me to see which is the correct limiting reactant and which one's in excess. Here's the same reaction but a different scenario. 12 moles of hydrogen gas and some oxygen gas are sealed up in what had been an empty container. After the reaction is complete, 8 moles of H2O are in the container and some hydrogen gas remains. Based on the theoretical yield, how many moles of gas were added to the container? If we look at the scenario, I think this is some information that we have. We have the amount of H2O that was produced. We know the amount of hydrogen gas that we started with. And the fact that some hydrogen gas remains tells me that the oxygen gas had been all used up. It was the limiting reactant. Pause the video. What are your questions at this point? If you don't have any questions, can you complete the rest of the table? Give it a try. Here's my thought process for completing the rest of the table. I finished with 8 moles of the H2O. I started with 0, so it must have gone up by 8. Once I have one value in the change line, I can get the other values in the change line by using the coefficients. And from there, I can finish it off. I can tell you how much hydrogen I'm left with, and I can tell you how much of the oxygen I began with. How many moles of gas were added to the container? I think it's 12 plus 4. This is the total amount of gas that was added to the container. Anytime I have a scenario like this to solve, I like to use a BCA table. When it comes to using BCA tables, once I began using them, I would use them and help students during office hours to try to explain what was going on. But as I became more comfortable with them, I found that they were my own strategy as well. So I'm not going to force you to use a particular approach, but anytime I'm asked to report more than one value, I find it's easiest for me to use a BCA table.